Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss thermodynamics in refinery and how it applies to process equipment. While most viewers of this video will have studied thermodynamics at university or while obtaining their STEAM ticket, few have understood it. That's because it was not explained properly. I can and will rectify this situation in this easy-to-understand short video. I will mainly be discussing water and steam. This is the working fluid that we on planet Earth have selected to run many of our machines and generate most of our electricity. The word thermo refers to the heat content of steam. The word dynamics refers to the velocity of steam. Thermo equals heat. Dynamics equals velocity. Why is thermodynamics important to the plant operator? Machines are not driven by the heat of steam, but by the velocity of steam. Mainly, I am referring to steam turbines used to drive pumps, compressors, air blowers, and electrical generators. It's the velocity of the steam striking the turbine blades that causes the turbine to spin. The greater the velocity of the steam striking the turbine blades, the more work can be extracted from each pound of steam. The application of thermodynamics in the process plant is intended to maximize the velocity of steam. However, the source of steam velocity does not originate with the pressure of the steam, but with the heat content of the steam. Hence, the original text on thermodynamics was called heat, a mode of motion. The term thermodynamics was introduced as an afterthought because it sounds more important. The source of steam velocity. Let's assume I wish to generate 1 pound of saturated 400 psi steam in a boiler. I'll be starting with a pound of water at 60 degrees Fahrenheit and atmospheric pressure. I'll do this in 3 steps and express the energy required for each step in BTU. Step 1, pump water up to 400 psi requires about 1.2 BTU. Step 2, heat water to its boiling point of about 440 degrees Fahrenheit at 400 psi requires about 380 BTU. Step 3, vaporize the water to steam requires about 820 BTU. Any boiler plant operator trying to optimize steam generation efficiency will worry most about the firebox and convective section economizer, and not the boiler feed water pump. About 2/3 of the energy required to generate steam is devoted to latent heat and 1/3 to sensible heat. The energy needed to increase the pressure of the water is very small in comparison. A hydroelectric power station generating electricity from a waterfall requires the flow from an entire river. A coal-fired power station generating electricity from steam requires a small water rate that could flow through a 12-inch pipe. The hydroelectric station is only using the potential energy of the water that has been converted to velocity. The thermal power station is using the heat content of the steam that has been converted to velocity. How to convert heat into motion? I have 2 ways of expanding steam. The bad way and the good way. In both ways, I am not changing the energy content of the steam. I am not extracting any work from the steam, there is no friction, and no heat is added or lost. This is called an adiabatic expansion. This picture illustrates the bad expansion. I expand 400 psi steam down to atmospheric pressure by going from a small pipe to a big pipe. That is, the cross-section area of the pipe increases to keep the steam velocity constant. This sort of expansion is bad because it accomplishes nothing. The velocity of the steam has not increased at all. It's called an Isoenthalpic expansion because the heat content of the steam has not been reduced. None of the heat has been converted to velocity. And since it is the velocity, not the heat, of the steam that does work, nothing has been accomplished. It's like taking a girl on a date to an expensive restaurant. At her front door, she says, "I had a wonderful time." Thanks. What have you accomplished? Nothing. Isoentropic expansion. I like to call the isoenthalpic expansion a parasitic expansion because it wastes the potential ability of the steam to do work. On the other hand, we have the good isoentropic expansion that maximizes the ability of the expanded steam to do work. This picture of case 2 also illustrates this sort of good expansion. This type of expansion is good because it increases the velocity of the steam. Thus, the question is, what is the source of energy needed to increase the kinetic energy of the steam? Accelerate the steam? Increase the momentum, mass times velocity, of the steam? This energy does not come from the steam pressure, but from the temperature of the steam. We are converting the sensible heat content or thermal energy of the steam to kinetic energy. It's like taking a girl home from dinner and she says, "Why not come up for a cup of coffee?" Comparing the two expansions in picture, the exhaust steam temperature has dropped from 330 degrees Fahrenheit to 212 degrees Fahrenheit, because the velocity has increased. The higher velocity steam can do more work than the slower steam. This single idea is the basis for the second law of thermodynamics, one of the fundamental principles that govern the dynamics of our universe. Cooling of steam on expansion. When steam is reduced in pressure, while maintaining a constant velocity, its flowing temperature goes down. How can the steam temperature go down without increasing velocity? Extracting work from the steam? Heat losses to the environment? The answer is that at a lower pressure the steam molecules move away from each other, which then lowers the frequency of molecules colliding with the temperature sensor. However, as the molecules move away from each other, the latent heat of condensation stored up by the molecules increases. In effect, just lowering the pressure without any change in velocity converts some of the sensible heat of the steam to latent heat of the steam, but without any effect on the heat content of the steam. This is also true for light hydrocarbons, ethane, propane, butane, but not for hydrogen. Converting latent heat to velocity. Reducing steam pressure from 400 psi down to 100 psi in an isoentropic manner, as shown in picture, will have two positive results. High velocity steam, at 100 feet per second, that can do work. 100 psi steam that I can use to rev oil distillation columns. But suppose I don't wish to use the 100 psi steam and would simply like to exhaust the steam to the atmosphere. Then, instead of the steam velocity being 100 feet per second, it might exhaust from the discharge nozzle at 500 feet per second. Where does all that extra kinetic energy come from? Some comes from a further reduction in the temperature of the steam. That is, the steam temperature will drop from the 440 degrees Fahrenheit supply temperature down to 212 degrees Fahrenheit as shown in picture. However, most of the extra kinetic energy of the steam comes, not from the sensible heat, but from the latent heat of the steam. To be precise, 10% of the steam will condense to water. We can extrapolate this concept further. Suppose I exhaust the steam to a vacuum of perhaps 25 inches of mercury, 30 inches being a perfect vacuum. Now about 15% of the steam would be condensed, and the steam, plus condensate, velocity might be 1,000 feet per second. I can extract much more work from each pound of steam. Of course, not only don't I have any useful steam left over, but I also have the expense of condensing the exhaust steam under vacuum conditions. See the Mollier diagram in picture. It's like the girl you have taken out to dinner asking, "What do you like for breakfast? Just coffee, or toast and eggs?" Note that, the numerical values expressed here are for illustration only. They are not correct in an absolute sense. You may study these concepts and arrive at accurate conversion rates of steam enthalpy to kinetic energy by using the Mollier diagram in your steam tables. Just follow the vertical isoentropic lines down the chart from the motive steam conditions down to the exhaust steam conditions. Note the lines of constant moisture as you drop below the saturated steam envelope line. Effect of wet steam. I suppose it may seem strange that creating more condensation of the mode of steam could allow more useful work to be extracted from the steam. But it was this particular observation that led James Watt to vastly increase the efficiency of the steam engine almost 200 years ago. On the other hand, moisture in the mode of steam supply itself is bad. As the steam is expanded to a lower pressure, the moisture in the supply steam will evaporate and cool off the steam, thus reducing the amount of sensible heat that could be converted to steam velocity. Momentum in steam turbines. A useful way of summarizing the concepts I have just related is to think about momentum. That is, momentum equals mass times velocity. When we operate a steam turbine, we are trying to provide a certain amount of horsepower to drive our pump, or compressor, or generator. If I want to provide this power with less mass of steam, I need to increase the velocity of the steam. And this is done by extracting more sensible heat from the mode of steam, and more importantly, more latent heat from the mode of steam. You can see quite clearly that it is not the pressure of the steam that is driving a turbine. Place a pressure gauge on the turbine case of a single-wheel machine. The pressure on the turbine case will be quite close to the exhaust steam pressure and certainly not the mode of steam pressure. Steam ejector temperature profile. The entire concept of thermodynamics, the conversion of steam heat into steam velocity, can best be observed on a vacuum jet. Let's say I have 150 psig or 10 bar saturated steam at 360 degrees Fahrenheit flowing to the jet. As soon as the steam enters the ejector through the steam nozzle, the steam cools off to about 90 degrees Fahrenheit. Don't take my word for it. Take your temperature gun and see for yourself. What happened to the missing 270 degrees Fahrenheit of the steam, 360 degrees Fahrenheit minus 90 degrees Fahrenheit? It was converted to velocity. As the steam slows down through the diffuser portion of the jet, you would expect the steam to partially heat back up. And it does, perhaps to 200 degrees Fahrenheit to 250 degrees Fahrenheit at the discharge of the jet, that is, at the condenser inlet. Rotoflow turbo expander. I did not understand thermodynamics at university. It seemed to be an exotic subject with no relevance to my future as a refinery process engineer. It wasn't until I had spent many years working with steam turbines, surface condensers, steam distribution systems, and most especially vacuum ejectors that I realized that without a firm understanding of thermodynamics, I could not operate or troubleshoot such facilities with any degree of confidence. For those of you who work in the liquefied natural gas industry, all the discussed principles relating to steam apply to light liquid hydrocarbons as well. The Rotoflow turbo expander, which you use to partially liquefy the natural gas, is much the same as a steam turbine. That is, the mode of gas is partially condensed to ethane and propane, as the temperature of the gas is converted to velocity, as the gas flows into the Rotoflow turbine case. Much of the torque developed by the expander turbine is derived from the latent heat of condensation of the liquefied petroleum fractions. The meaning of entropy. The second law of thermodynamics states that change in entropy equals change in heat divided by temperature, or ds equals dq divided by T. But what does this actually mean to ordinary people? Not people like Einstein or Edison or Marie Curie, but to people like you and me, who got a D in thermo? Entropy is a measure of the amount of heat that's available at a particular temperature. Lots of entropy is really bad. Heat available at a low temperature, which means the heat has lots of entropy, is bad. For example, let's say Paulie knows 100 girls in high school. Each girl likes Paulie enough to smile at him in the hall. This is like having a large amount of heat, but it's so diffused that it's almost useless. Having lots of heat available at a low temperature means the heat is so spread out that we can't do much with it. Paulie's problem is that his girlfriends are suffering from excessive entropy. On the other hand, Frank is involved with Kathy. All the other girls think that he's a nerd. But Kathy meets Frank after school so that they can study the history of art in Frank's room. This is like having a small amount of heat, but it's so concentrated that it's really useful. Having a small amount of heat available at a really high temperature means the heat has only a little entropy, which is good. I'll offer a better example of entropy. Let's say I've got 1000 BTU worth of heat in a big pot. But the temperature of the pot is only 68 degrees Fahrenheit. It's nice to have the heat, but at 68 degrees Fahrenheit, I can't think of any way to use it to make money. The problem is my pot has too much entropy. Alternatively, I've got a tiny pot with 100 BTU of heat. The temperature of this tiny pot is 2000 degrees Fahrenheit. I can use this heat to make steam, generate electricity, all of which I can use to make money. My tiny hot pot has very little entropy. Concentrating more heat in a smaller pot makes the stuff inside the pot hotter and reduces its entropy. And because concentrated heat with low entropy is easier to do things with than dilute, colder heat with high entropy, we say that increasing the entropy of heat reduces its ability to do work. 90+% of the energy of the universe is available at 3 degrees Kelvin or minus 270 degrees Celsius. That's the background radiation that contributes to static on your radio. This is the heat left over from the Big Bang, 13.5 billion years ago. But it's useless because it's so cold that all that heat has too much entropy. A small percentage of the universe's energy is stored inside stars in the form of gravity and hydrogen, which can fuse into helium, oxygen, carbon, iron, and people. That energy is available at tens of millions of degrees. It's really useful because it's so hot and thus has very little entropy. A process that takes energy in the form of heat and just lowers its temperature must increase its entropy. This is bad. A process that takes energy in the form of heat and converts that heat into momentum or kinetic energy does not increase its entropy, because when I reduce the kinetic energy, I would get all the heat back at the original temperature, provided the entire process was reversible, adiabatic. Expanding high-pressure steam to a low pressure through a steam nozzle used in turbines and vacuum ejectors as shown in picture is my favorite example of an isoentropic process. Almost all of the energy needed to accelerate the steam from 100 to 3000 feet per second comes from cooling the steam from 350 degrees Fahrenheit to 90 degrees Fahrenheit. In an isoentropic process, the heat content of the steam decreases, and its entropy is constant, provided that the process is fully reversible as shown in picture. In an isoenthalpic process, the heat content of the steam remains constant, and its entropy increases as shown in picture. The concept of entropy was not invented just to confuse young students by Professor Clausius. It was intended to define the efficiency of steam engines. Any portion of a steam engine that permits steam to expand and cool, without an equivalent increase in the kinetic energy of the steam, will increase the entropy of the steam and also reduce the steam's ability to do useful work, such as spinning a turbine's wheel or pulling a vacuum. When I used the word equivalent in the last sentence, I meant converting an amount of heat energy to speed, kinetic energy, or momentum. Thermo equals heat. Dynamics equals speed or motion. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.